So hello everyone, this is chapter 6 of chemical structure and reactivity. This is by your favorite lecture host, me. And right at the bottom we have a shout out list, so just want to give a heartfelt welcome to all these people on the list. Let's get into it. So, what this chapter will focus, it'll focus on what kind of bonding occurs in solids. So, if we talk about like chapters 4 and 5, we talk about bonding that happens in like these molecules, right? So we're talking like polyatomic molecular orbital theory, diatomic molecular orbital theory, all that jazz. Basically, this chapter will take in some concepts from the past molecular orbital theory chapters, and will introduce new concepts such as bands, which are especially useful if you want to ask, hey, I have a solid here, can that solid conduct electricity? And then we're going to go over some content going on to ionic solids. So overall, this chapter is actually kind of short, but it's still jam-packed with information, as is the rest of the damn book. So we're just going to go back all the way to the start, right? So chapter 1. Chapter 1 just mainly talks about like covalent bonding, different types of intermolecular forces, ionic bonding, metallic bonding, and atomic molecular solids. Just the fundamentals if you want to understand chemical structure and reactivity. So in chapter 1, I introduced the concept of solids and what the kinds of solids are that we refer to in the world of chemistry. So here are 4 kinds of solids. Ionic solids, so just think like pure table salt, NaCl. Now ionic solids, remember, general rule of thumb is that they form between a metal and a non-metal. That's just a general rule of thumb, however. And we also have metallic solids, which basically, if you have like a pure crystal, like take for example in this image, like pure palladium crystals, then what's been conceptualized is that we have some kind of sea of electrons, these delocalized electrons. Instead of being confined to each singular palladium atom, it's just a sea of electrons in a sea of nuclei, just like this delocalized bonding. And that will actually be like our foundation for band theory. So next we're going to go over atomic and molecular solids. So what these solids have are basically like discrete molecules or atoms that are held somewhat weakly together through intermolecular forces. So in these kinds of solids, all of them have London dispersion forces, which are formed from an uneven distribution of electrons, since these electrons have wave-like properties. But there can also be other kinds of bonding. So take for example something like ice. That's bonded in terms of IMFs with hydrogen bonds. And then we have covalent network solids, which are just covalent bonds that are extending through the entire structure. So take for example like something like quartz. I used to do if you guys know Science Olympiad, I used to do rocks and minerals. And literally like half the minerals I had to memorize, even just like a quarter of the rocks, that stuff was just SiO2 with some ions. That's just quartz. But if you look into quartz, you can see these covalent bonds just extended through the entire structure, not just these discrete molecules. So, now we're mainly going to focus on metallic solids and then ionic solids. And for this chapter, you'll mainly need your periodic table. You can just search that up online. Google has one. Some knowledge of past molecular orbital chapters. You can pull up those slides. And some basic atomic orbital concepts. So, now we're going to introduce the concept of bands. So, back in the last slide, I talked about delocalized electrons, which basically electrons are free to move throughout an entire sample of a metal. So, if we go back to something like chapter 5, this should remind us of those extended pi electron systems that we can find in molecules such as benzene and butadiene. Now, basically, what this means is these extended pi systems just kind of stretch along that entire molecule, right? So, since we have the concept of electrons being delocalized in metals, that should remind us of these extended pi systems. Now, let's take a chain of lithium atoms. So, lithium has 2 electrons in the 1s orbital and 1 electron in the 2s orbital. So I accidentally put 2d there. So, if you take a chain of them, we can find out that the 1s orbitals seem to be actually too small for any meaningful interaction. So if we take a chain of these lithium atoms, then only these 2s orbitals can create like meaningful interactions. They form molecular orbitals. So The lowest energy molecular orbital occurs with constructive interference between all these 2s orbitals, while the highest energy molecular orbital occurs with destructive interference between every 2s orbital. So that's something you need to know. So now we're going to introduce bands. So the reason why I included like 3 images here is because this part is like super visual if you want to learn. So if you see this top image is basically just like, here, what are the molecular orbitals that are formed if you have this chain of lithium atoms and we extend the number of atoms in that chain. So what we can actually see is that these molecular orbitals seem to cluster at the top and the bottom, which is also shown in the second image. From this graph that I've shown on the slide, you add more atoms, and at first this gap kind of increases, but you can see this gap sort of starts to level out. You can even see this in the second image. So this kind of width becomes independent of the number of atoms. And the reason is the number of bonding interactions in the most bonding molecular orbital goes to 1 as the number of atoms reaches of infinity. So if we take like some kind of limit, something that approaches to 1, logarithmic looking curve. So assuming that it has like an asymptote of y equals 1, we can set that limit as x equals infinity. We can set that limit, and as x approaches infinity, that gets like slowly and slowly closer to 1. So that's kind of what's going on here with the bonding interactions per atom. Now, you don't really need to like understand all of this. It's just like all you need to understand is that it levels out. Keep in mind that since the molecular orbitals extend through the entire structure of the metal, they're known as crystal orbitals. And these crystal orbitals form bands. Remember, orbitals can only hold 2 electrons per orbital. And these bands have a width of the gap between the most bonding and anti-bonding molecular orbitals. Now we're going to go on to how this band theory is associated with the conduction of electricity. So if you have, for example, some partially filled band, right? You have electrons in a portion of these crystal orbitals. So if we apply an electric field, remember that opposite charges attract, like charges repel, right? So this will create a shifting in the energies of these crystal orbitals. And since it's a universal law that everything wants to get to a lower energy, we can see these electrons kind of shifting from their crystal orbitals, from these current crystal orbitals, to these new crystal orbitals that are lower in energy. And this flow of electrons allows for conduction to happen. Generally, that's a good reason for why, because metals have partially filled bands. That's why, like, if you cut open a wire, you'll find metals like copper and silver. Generally, silver is the best conductor of electricity. Here's the first exercise I want y'all to do. But honestly, I don't really care. As long as you learn, it's fine. So, here's the problem. Would an empty band conduct electricity? And what about a few partially filled bands for you? And would a band filled 1/3 with electrons conduct electricity better than a band filled 1/4 with electrons? So we're going to start off with that first part. So an empty band. So let's think of it. If we have an empty band, so we have like no electrons in those crystal orbitals, and we apply an electric field, sure, the energies will change, but we don't actually have the electrons to shift in energy. So no conduction of electricity will occur. And this will also apply for a full band. Because with the full band, there's absolutely like no room for these electrons to move. Concerning that last part, would a band filled 1/3 with electrons conduct electricity better than a band filled 1/4 with electrons? That generally does not matter. Because all that matters is that the band is partially filled. That's all that matters. So we're going to go on to more band theory. So, unfortunately, even though I like to expand that band concept to a full 3 dimensions, I've only been talking about this in sort of like a 2-dimensional form, or lower dimensional form. I just can't talk about that. My brain would explode, and you can take that from the authors themselves. So, now, instead of lithium, let's go on to beryllium. So that's 2 electrons in that 1s orbital, and 2 electrons in the 2s orbital. We're going to have a fully filled band. So, beryllium is not a conductor, No, this is actually not true, because beryllium actually is a conductor, because there's an empty band that overlaps with a 2s band formed from the 2p atomic orbitals in the metal. So this is a big relief, because we now get two bands that are partially filled. And this also means that beryllium is better than lithium for conduction. So we can see this S band and P band. So the reason the P band is empty is because there are no electrons in the 2p orbital concerning beryllium. But you can see that they overlap, and these electrons from the S band migrate over to that P band because everything wants to get to a lower energy. So it's true that, yeah, beryllium is a conductor now that we have this in place. So I've only talked about bands formed from atomic orbitals like 1s, 2s, and 2p. However, kids, don't fear, molecular orbitals will always be mentioned in this book. So let's take an example for a solid. So take, for example, solid hydrogen gas. So what solid hydrogen gas is, basically, you need to cool that thing down to like 16 Kelvin, like super freezing frigid temperatures. Now, we know that hydrogen gas has two electrons in that sigma bonding orbital and none in the sigma anti-bonding orbital. So, from each of these orbitals, we obtain a band. So, generally, the solid is an insulator, as we have a fully filled band and there's no overlap. However, at high enough pressures, the bands overlap, leading to the solid to be a conductor. In this case, I've actually read this online. It not only can be a conductor, but a superconductor. And we can see from this image, we get that narrow spacing. We still get that gap. And we also get, our sigma, our bonding and anti-bonding crystal orbitals from both sigma bonding and sigma anti-bonding. So that's something I wanted you guys to know. So, band gaps are especially important, especially when you're talking about like stuff like silicon, right? So, what a band gap describes is basically the distance and energy of a fully filled band in relation to an empty band that's higher in energy. So it's a major indicator of whether or not a solid is an insulator, a semiconductor, or a conductor. Now, honestly, I wish I can get into how they calculate the band gaps. However, I did search it up. There's a thing known as the Todd equation, but I'm not going to cover that, mainly because that's going to require a good portion of extensive physics knowledge that I just won't get into. So, this full band is known as the valence band, and the empty band is known as the conduction band. And if you have a small enough band gap, right? Like the bands are not overlapping, but if you have a small enough band gap with enough thermal energy, electrons from that valence band can be promoted to the conduction band. And semiconductors possess this property. So, unlike conductors, they don't conduct electricity as much as to an extent, but unlike insulators, they just don't totally block electricity. So semiconductors possess this property. So take, for example, silicon. Y'all are operating on silicon-based machines right now. So this is especially important, band gaps in semiconductors. So let's go over this again. Insulators have a larger band gap. Semiconductors have a somewhat small band gap. And conductors have overlapping bands. So right here are the calculated band gaps for certain solids. Now, here's the thing. Would you expect beta tin to conduct electricity at a better capacity than alpha tin? And you have to explain your reasoning. So using this band gap concept, we can see that beta tin has a lower band gap than alpha tin. So, alpha tin is actually a semiconductor, because electrons can still be promoted to that conduction band with enough thermal energy. But for beta tin, you don't even have to do that. Electrons just flow. So yeah, beta tin is a better conductor than alpha tin. Next, we're going to go over graphite, one of the greatest allotropes of all time, and it's just like something that's changed education for the better all time. So this is unlike diamond, because this can actually conduct electricity better than diamond. So if you've taken like any kind of electrochem experiments, electrochem labs in your high school, college chemistry courses, I know for some diagrams they may have included sticking like pencils up to your electricity source. And pencils contain graphite along with a mixture of a few other things. So anyways, graphite consists of singular layers of sp2 hybridized carbons with unhybridized p orbitals with a single layer known as graphene. So basically, graphite's just stacks and stacks upon with these graphene layers, and they all are hexagonal in nature. And we have these hybridized p orbitals like reaching outside of that graphene kind of plane. Unhybridized p orbitals, yeah. And so this net of carbon atoms has a unit cell, which is basically a pattern that can be tiled to form this surface, containing only two carbon atoms at opposite corners. Now, this extended pi system will be explained with band theory. So, the bonding pi band is full, with a small gap between it and the anti-bonding pi band. However, this conductivity is confined to layers of the graphite, meaning that this property is anesotropic, which basically indicates that it does not have the same qualities in all directions. So, finally we're out of metallic hell, and now we can go over to ionic solids. So, basically, ionic solids are held by the electrostatic interactions that are present between cations and anions. We can also define something known as the lattice enthalpy, which is the energy change that occurs when the ions in their gas phase are brought together from infinite separation to form that ionic solid. Just think of those ions just coming together to form solid in gas phase. So, the last energy is negative, because we can expect a reduction in energy. And for the ions that are brought together in order to form the ionic solid, we also assume that the ions the gaseous form are at absolute zero. So that's just a fun fact you need to know. Now, how we determine this lattice enthalpy experimentally is we use something known as the Born-Haber cycle, which is just basically a graph or diagram showing you the overall enthalpy change. Now we're going to go on to the ionic model for lattice enthalpies. So the attractive force of two opposite charges is proportional to the function 1 over r squared, which r is just simply the distance between them. However, if this were the only force, if that attractive force was only present, the ions would just smash into each other. So there must be some other force for these ionic solids to form in these nice orderly lattices. So we thus calculate the energy of the ions instead of the force that is, with the potential energy being proportional to negative 1 over r. You don't have to memorize all these equations though. So there's also repulsive interaction that increases as the ions get closer to each other. So this is caused as if a filled orbital interacts with another filled orbital, we'll get the creation of an antibonding and bonding molecular orbital. And this antibonding molecular orbital is a lot higher in energy. And if you keep bringing these ions together, that antibonding molecular orbital is just going to skyrocket in energy so much more quickly. So, it's found that the potential energy of this interaction varies as 1 over r to the power of n, where n ranges from 9 to 12. So right there's the graph for you. I'll hold it up on screen for a minute. So next we're just going to go on to the energy of a chain of ions. Now, the potential energy in joules of two ions, Z1 and Z2, that are separated from distance r is denoted by this equation. Now, it's a lot to take in, but basically it says Z1, Z2 times the fundamental elementary charge, which is this amount of joules. Honestly, you don't have to memorize this. All you need to know is that equation. Now, using the knowledge of basic charges, we can see that when focusing on one ion, there's an attractive interaction from that ion to the other ion. But there are also repulsive interactions, because if we focus on like this ion, for example, there's also, and since we have that repulsive interaction, we include this positive term. And we have twice the number of both attractive and repulsive interactions. And if we sum all these equations, we get this total energy, which is, yeah, a total mess. So if we try to clean this up with using some simple algebra, we get this sum, -2 times that equation I showed you, times 1 minus 1/2 plus 1/3 minus 1/4, and so on. So that value in the brackets equates to the natural log of 2, which is 0.693. And if we multiply that by 2, we get the Madelung constant, which is 1.368. But this will depend later once we extend our ionic concepts to 3D. To go on to more equation derivation. So, this first equation utilizes the Madelung constant in conjunction with Avogadro's number, because we want to get the energy in kilojoules per mole here. So we can see our first equation. And now our second equation accounts for our repulsive interaction. So we have Avogadro's number, R times N. Remember, N varies from 9 to 12. And C just being constant. Now if we clean this up using some calculus, we get this equation. So it's the negative of Avogadro's number times the Madelung constant times the complicated random jumble of math that I showed in previous slides times 1 minus 1 over n. Still remember, n varies from 9 to 12. So here's our third example. So, potassium iodide is especially useful in a biological sense, as it can help the thyroid gland, which is present in your neck area, whenever there's a threat of radioactive iodine in the body. So, the equilibrium distance, which is RE, I forgot to mention that, is approximately 305 picometers. So from this, calculate the energy of a chain of ions in potassium iodide, with N at a value of 9. So right here, we have the energy, we have Avogadro's number, the Madelung constant, and Ki, that's just 1. We multiply that by the elementary charge squared, and over that we get 4 pi times the E epsilon 0, which is basically just permittivity of free space, times that equilibrium distance. And we multiply all that by 1 minus 1/9. Now, honestly, when we equate this, we get around negative 553.8 kilojoules per mole. Honestly, how to equate this using Desmos. But yeah. So now we're going to go over 3 dimensions. So, as we go on from extending that concept from a chain of ions to a 3-dimensional lattice, the value of that Madelung constant is the only thing that will change in this calculation. So, this table will also show the coordination numbers. This table I have here. I'll show the coordination numbers for both cation and the anion, which indicates the number of ions that's bonded to. And now we have this equation on the bottom, which is now modified to calculate lattice energy for 3D ionic structure, with a generalization now, with charges being independent set squared. So next we're going to go over ionic radii. This is a super simple concept. So basically, the interionic spacing in an ionic solid can be thought of as a contribution of ionic radii, which is basically just the distance from the nucleus to the outermost shell of the ion. So all you need to know is electrons make you fat, and the more electrons you lose, the smaller that you are. And you can actually see this. So take, for example, this third period. So, as you can see, we have the sodium ion, which just has 1 electron ionized, 116. But I have the magnesium ion, that's 86. Big shocker. That's actually just like a massive decrease. Now, if we compare the sulfide ion and the chloride ion, we can see that the sulfide ion has more electrons, and electrons make you fat, so that's why it has a larger size than chloride ion. Now next we're going to go over the Kapuscinski equation. So basically, this Russian chemist, he produced a simple way to approximate the lattice energy and found that the ratio of the Madelung constant and the number of ions in one molecule of an ionic solid, like NaCl, you have 2, 0.87 more often than not. And using some calculations, the end equation is the energy of the lattice is approximately equal to the negative of 1.07 times 10 to the 5 times the number of ions times the charges. And overall of that, we have the ionic radii added up together. Now, this is a simple approximation, and generally it gets to a 5% range, honestly, in my experience. This is mainly just plug and play. So, Using the chart that I've given you, use the Kapustin-Key equation to calculate the lattice energy of the most ionic compound, which is cesium fluoride. So we have this equation, E lattice, approximately. So we know that N ions is 2 because cesium fluoride, if we take 1 unit of that, there are 2 ions in there. And we also know that there's 1 and 1, because cesium has a +1 and fluorine has the -1. And then we put all that over that picometer indication. So it's just 181 plus 167. And using Desmos, I found out that the predicted lattice energy was around 713.33 kilojoules per mole, which is within that 5% range of the true lattice energy, which is negative 744 kilojoules per mole. I just got that from Pearson textbook, by the way. So this equation is actually more so an approximation, I've told you, right? And this means that this is chemistry, there will be exceptions. So we're going to just end this off with the validity of the equation. So I'm just going to keep it short and simple for you. The greater the covalent contribution in an ionic solid, the less able the Kapustin-Key equation can predict it within the desired range. So you can see for the group 1 halides, there's not as many covalent contributions as we take like copper 1 halides, silver halides, and thallium 1 halides. Because these 3 groups have more covalent contribution than our group 1 halides. So that's mainly the end. I hope you liked it. And for a sneak peek, finally we get to exit bonding and go into thermodynamics. Just kidding. I'm just kidding, man. This book's all about bonding. So in the next chapter, we'll just talk about like entropy and Gibbs free energy, which are 2 essential concepts that you'll need to understand for thermodynamics, and a whole lot more. And this will also be useful in the prediction of equilibrium, which will be talked about in the next chapter.